So my name is Paulo Mendes. I'm a doctoral researcher for the Faculty of Engineering, University of Porto. And I'm here to present you my work, which is entitled as Ice Cycle Fatigue Design Curves of Build and Ice Transfer Skills for Offshore Applications. So to start, this will be the contents of my presentation. I'll start by doing a brief introduction regarding the background and the motivation of the study. Then I'll describe the materials and the experimental details that are associated for this work, and describe the methodology which was applied for these design curves, which is the probabilistic strength modeling. And in the end, I'll present you the rightful conclusions with a summary of key findings. So to start, offshore installations are exposed throughout their life to cyclic environmental loading, which causes cyclic variation in its structural members. This cyclic environmental loading is the main responsible for fatigue. And fatigue is the leading cause of incidents for offshore systems and wind turbine systems, that you probably already know. And you can see from this table from the literature. There is a wide range of uncertainties associated with the fatigue analysis of offshore structures. And while these factors are all crucial for this fatigue analysis, my research work focus mostly on the material characterization through probabilistic fatigue strength modeling. So this is the framework that summarizes really briefly this research work. We decided to opt for two regression methods, the classical linear regression method and the orthogonal linear regression method. We also applied the ISO 200-107, which is a commonly used standard to plan the statistical data for fatigue. We use the two variable distribution, which is also applicable to modeling lifetime data and for liability analysis, and the method of estimation for the two parameter variable distribution, because the two parameter variable distribution has two parameters, which are the shape and scale parameters, was the maximum likelihood method. And we also applied the Castillo and Fernandez-Cantelli model, which is a non-linear model usually applied for the ice cycle fatigue regime, and a Bayesian inference with the Markov chain Monte Carlo simulation using normal distribution as a prior distribution. So now talking about the materials and the experimental details that were applied for the design curves. So Dantas et al. Evaluated the SG55 steel G2 mill steel through uniaxial fatigue tests. These uniaxial fatigue tests were performed under different stress ratios, as you can see from the table. So since we had some stress ratios with a 0.01 stress ratio, we needed to account for the mean stress effect. So Dowling has a really nice work where he did a comparison with different materials and different curves that are in the literature, formulas from the literature, which allow us to account for the mean stress effect. So I used the Walker equation, which is suitable for this type of steel, the SG55 steel, which allow us to convert a stress cycle into a stress cycle without the mean stress effects. With this, I mean, we convert a stress cycle into fully reversed conditions, as you can see from this example. Also, the S690 base and welded steels were object of study using rotating bending fatigue tests. So note that when we are performing rotating bending fatigue tests, this type of tests occur with a stress ratio of -1. So we didn't need to account for the mean stress effect. A total of 56 specimens for the base material and 26 specimens for the weld material, according to the S690 QL. These specimens were extracted from two different welded joints. But if you need more information regarding the experimental campaigns, feel free to ask me later, because these works are already published, so feel free. Now, going for the probabilistic fatigue strength modeling. So we used, as I stated earlier, two different regression methods. The one you probably already know is the classical linear regression. It's also known as the ordinary least squares method. It asymmetrically relates X and Y, where it seeks to minimize the vertical distances in Y or the horizontal distances in X. And then we have the orthogonal linear regression, which is also commonly known as well as total least squares method. This method seeks to minimize the orthogonal distances between the data points and the regression figure line. So we can achieve a linear relationship between the number of cycles and the stress amplitude through this equation. And if we apply the two regression models and the three probabilistic models, because these three probabilistic models are related to the regression methods, except the Castilian-Fernandez-Cantelli, which is a nonlinear method, we can relate A and B with the Baskin's law, which is a commonly known stress local approach to estimate the fatigue material properties. In this case, the fatigue strength coefficient and the fatigue exponent. So these were the results that were obtained for these three materials, according to which probabilistic method. I forgot in this presentation today, I was thinking, I forgot to put the Castilian-Fernandez-Cantelli results. But we also performed for three different probabilities of failure. We performed for the mean curve, so it's basically the mean curve. And then we did these for two probabilities of failure because the DNV, GL, and the Eurocode 3 provide design curves for 2.3% and for 5% respectively. That's the reason why we did these curves for these probabilities of failure. We also calculated the coefficient of variation. The coefficient of variation is really useful for reliability purposes and reliability design. So moving to the curves, we found out that when we did the comparison between the curves, we found out that for the classical linear regression, the two-parameter variable distribution is the most conservative fit. And for the orthogonal linear regression, we found out that the Bayesian method was the most conservative curve, and therefore the two selected curves for these methods. Since we are talking about offshore structures, it is important to note that corrosion also has some effect. So based on the same stress local approach, Adazoria introduced an equation to account for the corrosion effect. This formula needs to have the constant amplitude fatigue limits under corroded and uncorroded conditions, the ratio, as you can see here, the C variable. And since we didn't perform any corrosion fatigue test, we needed to have this data, this information. So in the literature, there are some work regarding this relationship between the ratios of the constant amplitude fatigue limits under corroded and under corroded conditions. And these were the values that were chosen and selected according to the literature. And we selected these two models, as I stated earlier, mostly because of the material applicability, because we are talking about offshore structures, and offshore structures are exposed throughout their life to high frequency loading, but with low stress. So these were the derived curves now under corroded and corroded conditions, as you can see at the top. We also found the need to generate some postulated corroded data points. And these postulated corroded data points were generated based on the root mean square error between the probabilistic models and the data points. And since we are performing here design curves, we had the need to also account for a full range SN curve that accounts also for the variable amplitude fatigue limits. In order to account and estimate these variable amplitude fatigue limits, we took into considerations the DNVGL standard and the Eurocode 3. And this is the proposed equation in order to estimate the inverse slope of the variable amplitude fatigue limits. So this is it. For my conclusions, we found out that the orthogonal linear regression analysis showed a more conservative fit compared to classical linear regression, mostly for the low cycle fatigue regime. So I know that this is not really important for this work because we're talking about high cycle fatigue regime, but it was important for me to point out. The two-parameter variable curve using the classical linear regression analysis showed a more conservative fit for the medium and high cycle fatigue regimes. Okay, take in mind that this was my selection for the low, the medium, and the high cycle fatigue regime. I know that in the literature there are some authors who can probably change a little bit in terms of intervals, and we also found out that the Castillo and Fernandes Cantelli model provides some advantages. It can estimate accurately the constant amplitude fatigue limits, but the vertical asymptote, mostly correlated to the low cycle fatigue regime, can yield some non-conservative results, as you can see from these 2 data points, okay? Also, the corroded curve displays a steeper curve, but I think you probably already knew about this, which indicates accelerated degradation. And note that the S690QL, since it had a lower ratio between the constant amplitude fatigue limits and uncorroded conditions, this S690QL curve has a steeper curve compared to the S355. So we can say that the S690QL is more susceptible to the degradation through corrosion than the S355. So to conclude and to give more practical implications from this work, we can say that in the fatigue design, when we are dealing with new systems, we should apply the classical linear regression combined with the 2-parameter variable distribution. However, when we are dealing with data from long-operated materials and structures, where the data uncertainty, there is some data uncertainty to the fatigue load and to the response, we suggest the orthogonal linear regression. For this, for example, for retrofitting purposes. So with the retrofitting purposes, we can allow for some accurate life extension without compromising the integrity or safety of retrofitting projects. So this is it. I hope you enjoyed my presentation. If you have any questions, suggestions, anything, please feel free to talk. Thank you.